Okay, this is the range of power factor from 0 to 1. So it can be said leading or lagging. Okay, leading power factor means that current lead voltage. Okay, it's always based on current. Current leads voltage. Okay, which implies that when we have a capacitive load. For lagging, it means that current lags voltage. Okay, you can go back to topic 5 in page 46, 47, 45, 44. Okay, to see how the current lag voltage. Okay, the explanation is there. You can go back to topic 5. Okay. So power factor will influence the electric bills. As I said earlier, if it has value below 0.85, there will be penalty that the company should pay. Okay, let's go to steps to determine leads or lags using phasor diagram. Make sure the amplitude of the expression is positive value. Use the following to change from negative to positive. For example, minus sine A, so it is sine A plus minus 180 and minus cos A. Okay, then it's cos A plus minus 180. Make sure the function is in sine function. Okay, you know how to convert. This is the conversion from cosine to sine. Okay, it's always plus 90 degree. Okay, then we can draw the phasor diagram. Okay, leading direction, okay, is always from 0 counter clockwise. Okay, this is the leading direction. Okay, while for lagging direction it's clockwise direction. Okay, so from here we see Vm is at the leading direction and Im is at the lagging direction. From the phasor diagram, okay, the rotation is always clockwise. Okay, it started from this real axis. It rotates from here to 360 degree. Okay, rotate both of the drawn expression to determine the leading or lagging of our factor. We can see the position from here. I is lagging. So you can see that it is a lagging power factor. Okay, I lagging here. So this PF is lagging. Okay, let's take a look on this example 4. Given that current and voltage for series connected load. Okay, this is the current and voltage here. And we see the angle of the current is positive 10 degrees, while the voltage, the angle is minus 20 degrees. So from here we can know that I is leading the V. Okay, so I leads V. So from here we need to determine the apparent power and the power factor of the load. We determine apparent power. We use power equation S equals to V times I. Okay, so this is VRMS. We need to divide by square root 2 from the maximum value. This is maximum value for current, maximum value for voltage, and we divide both and we get the apparent power and then multiply the apparent power is 240 VA. Okay, to find the power factor, which is cos theta. Theta is the difference of the phase angle between these two. Theta V minus theta I. So cos of that is 0.866. You can verify this calculation later. So in this example, the power factor is leading because current is leading the voltage by looking at the sign here, positive or negative. Okay. Then the load impedance Z can be modeled by a 25.98 ohm resistor in series with a capacitor. Okay, because we can calculate the impedance value, which is V over I. So from this calculation, we get this impedance value, which is, as you know, this is R and this is X. So from here, we can determine the capacitor value in this circuit, because we know when PF is leading, then the load must be a capacitor. So we need to know the value of the capacitor. So now we have the capacitive reactance value, which is 15 ohm here. So use this equation, xc equals to minus 1 over omega c. So just move this around and we get the capacitor value of 212.2 microfarad. Okay. The most important thing here is you need to familiarize yourself with this complex number of phasor calculation, even by using a calculator. Next, let's take a look on example 5. Determine the power factor and average power delivered by the source. We have V RMS here, 30 volt RMS, 0 degree R here, and we have 4 ohm and minus J 2 ohm. Okay, from here, we determine the total impedance. So we know these two is in parallel, so do the parallel calculation here, and plus R, and finally we get the impedance is 7 at the angle of minus 13.24 ohm, 24 degrees. Sorry. So from there, we can determine the current of the circuit by using V RMS over Z. Okay, so we can get the current RMS current, and then from there we can determine the power factor. Okay, the angle of voltage here, the angle of current, this one. So theta V, theta voltage, minus theta for current. So we get 0.9734 power factor. So how we can know it's leading or lagging? So we can compare here. Okay. We draw this diagram. V is here. V is on this axis. V, and I is here. Is 13 degree. 13.24 degree. So we can see here I is in front of V. So it is a leading power factor. Okay. If I before V, okay, in the direction of anti-clockwise, then it is lagging. But now it's leading here. Okay. So to determine power, just use this equation: P equals VRMS, IRMS cos theta V minus theta I, and finally we get the answer, 125 watt. Okay, you can try by yourself this example to determine the power factor and average power delivered by the source. Now let's take a look on complex power. It is a product of RMS voltage phasor and the complex conjugate of the RMS current phasor. As a complex quantity, it is real part is real power and imaginary part is imaginary power or reactive power. Okay, it's not the power that do the real work. What I mean real works is you can imagine if you have a fan. So the real work of fan is to move the blade, right? So it can blow uh, the air. Okay, so that's the real power. But what is not real? But what is the reactive power in fan is the voltage and current needed to generate the movement. Okay, the movement was generated by using electromagnetic. Okay, it's a magnetic force actually. When the current flow will generate electricity, generate the magnetic field between two components, the moving and the static component. Okay, so it will move and rotate the shaft of the fan to move the fan. Okay, to rotate the fan. So that's the power. That's what's called reactive power. Usually it is referring to power and voltage at the coil, okay, in the fan. Okay, so let's consider this two the following equation V and I. Okay, power equation is always V times I. So here to find the complex power, okay, V times I conjugate. This symbol is for conjugate. Okay, complex conjugate of the RMS power phasor. Okay, so what does it mean by conjugate? You change the polarity. Okay, if it's positive, then change to negative. Okay, so for theta I here, it becomes negative. Okay, because as you know, the multiplication of these two is V must time I, and I theta V is plus theta I, but the conjugate of theta I is minus theta I, so it becomes theta V plus minus theta I becomes theta V minus theta I. This equation. So V times I is S. Okay, and finally we get P and Q. We convert from uh, rectangular to polar form. Okay. Okay, as written in the earlier slide here, where Q is the reactive power. The unit is VA reactive, VAR. Okay. Unit for S is VA. Okay, S unit is VA. P is in watt. Okay, and Q is in VAR. If Q equals to 0, the power factor is unity, means that no reactive power. Okay, the load is fully resistive. It's not inductive, no capacitive. Okay, if Q is minus, negative, it's leading power factor and it must be a capacitive load. If Q is positive, more than zero, then the load must be inductive load. Okay, it's a lagging power factor. Or simply I lead V and I lag V for Q minus Q positive. Okay, let's take a look how to imagine it as a power triangle.